Hey everybody, let's talk about Lab 2. Welcome back to class. Before I start, I'd like to give a little disclaimer. For this video, I'm just going to do it in one take. I'm not going to edit it at all. And my reason for doing that is hopefully to show you that there's still a human interaction element to this class. And I want to make sure that I show you guys that I make mistakes, because one of the things I want to stress, and especially is important in labs, even though we're not in the lab working with our hands, working with the equipment, is that it's okay to make mistakes. That's something that I think isn't said enough, and I'd like to share with you all, is that it is absolutely okay to make mistakes. What's not okay is if you're not learning from your mistakes. So every mistake is, anytime you make an error, every mistake is the opportunity for you to grow as a person, as a student, as a learner, or in any aspect of life. So that's why I want to show this all in one take, because if I make a mistake, I want to show you that it's okay. So keep that in mind while you're working through these labs. It's okay if you make mistakes. It's okay if you struggle on this stuff. All I ask is that you try to learn from those mistakes, that you try to grow as a person, that you try to learn more. So keep that in mind as we go through. Now, that being said, I give this introduction about mistakes because there is a little bit of a mistake in the video that I'm going to post along with this video. And I want to cover that, amend it so that you're not confused on the lab. Okay. So I wrote myself up a little list of things I'm going to talk about so I don't get too distracted. I'm going to overview what lenses are. That's what this week's lab's about. We're going to talk about the lens maker formula. I'm going to give a little example of that. And then I'm going to give you sort of an overview of the 3 procedures. And then I'm going to point you next, after you watch this video, point you to the video that Sean made. That's the one that, or the ones that all of us TAs made together. He's just the one talking in it. And so you can watch through that one so you can see the actual procedures happening in the lab, because here I'm just going to draw the procedures on my whiteboard and talk about them. But I want you to see what it looks like when they actually have a lens and a laser and they're doing stuff in the lab. So watch the procedure part. Feel free to watch his theory introduction as well. It's just going to be similar to the stuff that I talk about, but it's always good to hear it from multiple sources. Sometimes you pick up on things differently when you hear it from different places. Okay. So after that, then I'll post a data sheet, and for this week's lab, you're actually going to turn in your data sheet because you're going to have to write down your 2 observations that I'm going to talk about in this video, but I'm not going to write in the data sheet. The rest of the data, the numerical data, that'll all be in the data sheet that I upload, but there's going to be 2 spots, namely in procedure number 1, part C and part D, that you're going to have to make an observation on your own, write it in your data sheet. And to make things a little bit easier, if you don't want to upload a whole data sheet, like trying to convert it to a PDF, or I guess downloading my PDF and adding your own text to it, if you don't want to do that, you can include just a single section above your analysis questions or above your regular questions that says procedure observations C and D. I'm pretty flexible on how that works, and if you have any questions, please feel free to email me. If email is too hard to work with, feel free to email me about setting up a Zoom meeting, and I'd be happy to come talk to you face-to-face over Zoom. I wish there was a better way, but Zoom seems to work pretty well. We've been using it for some of our classes. So yeah, if you want to talk, send me an email. We'll meet over Zoom. Okay, let's start. So, talking about lenses. What are lenses? So, the most general definition of a lens I can think of is pretty much any sort of transparent material. Anytime light goes into a material and comes out the other side, that's considered a lens. So even the acrylic block that we used in last week's lab, just that block where light was coming in, coming back out the other side, that's considered a lens. Now, it's a really boring lens. The reason for that is this surface is flat and this surface is also flat. So when the light goes through, nothing changes about the light. It just comes straight back out. Even if you send it in at an angle, it gets bent while it's inside there, but it comes out net at the same angle. Okay, what gets interesting about lenses is when you start introducing curved surfaces, non-straight surfaces. You can make a really crazy lens with some crazy jagged surface, and it would probably do something really crazy with the light, scatter it all over the place, and it might be cool. But it's not usually so useful. So most of the time we use curved surfaces, and most of the time we actually use spherically or circly curved surfaces. So it makes a circle out of that part of the surface. So this is what I'm talking about. Let me erase that. let's say my lens has a surface that's curved like that and a surface that's curved like that. I'll just connect those up. Now, my drawing's not the best, but imagine that these actually were parts of a circle. So if I trace this out, pretend that that's a circle, and then this surface also makes, it's part of a circle. It's a slice of a circle. Okay. Now what happens if there's two circularly curved surfaces on either end of this lens? Well, you actually get something quite interesting. If you send light in like this, say I've got 3 rays coming in, and we'll say that this middle one is right along the center of this mirror, or sorry, not mirror, of this lens. What actually happens is the light will get bent and all converge at a point somewhere outside the mirror, or the lens. Something like that. So after the light passes through, let me erase that. Because really what's happening inside is it gets bent a little bit here at this surface, gets bent a little bit more at this surface. This ray is right in the middle, so it actually goes straight through. This ray is bent a little bit here and bent a little bit back up that way. Now my drawing's not perfect. They've got a much better one in the lab manual, so I recommend taking a look at that. But notice here what we've done is we've taken all this light and we've converged it to one point. Now this might not seem like it's that useful, but we actually use lenses all the time. And in fact, you guys use 2 lenses every day, your eyes. So our eyes actually behave like a lens. And basically what we need for our eyes to work. So pretend this is my eye, right? This is where the light comes in. In order for me to see an image clearly, something that's in focus, all of the light coming from that image, so let's say maybe this is like maybe there's a person over here, and I want to focus my eyes to see this person, right? All the light coming from this person and entering my eye needs to focus, and what I mean by focus is converge. It's to converge exactly on the back of my eye. Now, someone who's more familiar with biology may know a little bit more in depth about how this works, but for now, just think of it as everything needs to converge at a certain spot in my eye in order for me to see this person clearly. Okay, so our eye actually functions as a lens. What's cool about our eye, though, is we can actually change the focal length of our eye, of our lens right here. So let me, I forgot to write that down. So this right here, this point where everything focuses to, that's called the focal point of the mirror, or of the lens. Sorry about that. So this right here, that is the focal point. And we say that the focal length of the lens is the distance from the center of the lens to the focal point. And we call that lowercase f. That is the focal length. I ran out of room there a little bit. Focal length. Okay, hopefully that makes sense. Let me make sure that's clear. Good, okay, you can read that. All right, so we got our focal length of our lens, we got our focal point. Now our eyes can adjust the focal length of the actual lens that's in the front of our eyes in order to adjust where this light hits in our eye. So if I was looking at something that was a little bit further away, my eye can actually change the shape of its lens, change the focal length in order for something that's a little bit further away to hit, to all focus right in the back of my eye. Okay, now what happens when someone needs glasses? So when you need glasses, there's a couple different things you can be. You can either have your eye focuses your light too far away, too much to the inside of your eye, or it could focus the light too far away on the back side of your eye, which means that everything, either one of these situations will look out of focus. So, for example, if my eye was focusing all the light to this point instead of right onto the optic nerve in the back, what I can do is put a pair of glasses or put a convergent lens right in front of it. So if I put a lens like this right in front of my eye, now the light coming through this lens, and as long as I get the focal length of this lens right, this lens can actually force the light to go all the way to the back of my eye. Now I apologize, my lines right here are not very straight, but I hope that the idea makes sense. Okay, so that's a little bit about lenses. There are a bunch of different types of lenses, depending on if you play around with what shape is on each surface. So this right here, this is a convex lens. Convex. The way I like to remember that is this type of lens converges the light, so converges, convex. Another type of lens is a concave lens. These are the two that we're going to be working with today. And that looks like this. The way I like to remember this is that the openings look like a cave, but that sometimes gets confusing because these sort of look like a cave too. So I like to remember it by converging lens, convex. I use that V, conv, to remember it. Okay, so how does a concave lens work? I'm going to go ahead and take these lines out of here so we can compare. So if I send in the same 3 lines right here, 1, 2, 3, what happens to each one of these? Okay, so pretending the middle one goes right through the center, it'll come out straight. But these ones actually get diverged, opposite to how this get converged. So these diverge out like this. Boom. So now, I want to ask, where is the focal point of this concave lens? Now we said that the focal point is where all the rays meet, and it looks like none of these meet. Well, they actually do, just not in real space. They meet in imaginary space, so like this. So if I trace these lines backwards, we see that these all meet right here, or they would meet. Remember, there's not actual light going at this point, but this is where we say these lines would meet if we extend them backwards. And because of that, that's what we call the focal point of a concave lens. So remember, so this is the focal point here. All right, let me double check to see if that's in frame. Okay, good. Okay. Now, and so same as up here, the focal length is the distance from this point to the center of the lens in here. That's our lowercase f, that's our focal length. Okay, these are the 2 types of lenses that we're going to be using in this lab. Just to point out, you can make other types of lenses. You can make like a planar convex, which looks like that, where it's got a plane on one surface and a convex lens on the other, or a convex surface on the other. So any combination of surface types you can turn into a lens, but these are the 2 we're going to focus on. Okay, the last thing that I need to talk about, actually we'll move on to lens maker's formula now. Okay, so remember this is our convex and our concave lenses. Okay, convex, convergent, concave, divergent. All right, let's move on to the lens maker's formula. Okay, I'm going to go ahead and leave these up here actually, and we'll talk about it this way. So the lens maker's formula is a famous physics equation that tells you the focal length of a lens based on how the 2 surfaces work, or are shaped. So each surface here, I guess I'll just draw these back in. Each surface is said to have a radius of curvature. Now what I mean by that is that I said before, each surface behaves like it's part of a circle. And so the radius of curvature is actually the distance from the surface of that piece of the lens to the center of its circle. So let's say that this is the center of this dashed circle. The distance from this surface to the center, right here, this distance, that is the radius of curvature of that surface. So let's see. I ran into myself again. Okay. So our radius of curvature is this distance right here. Boom. Now, similarly, this surface has a similar radius of curvature. If I draw this in, it's the distance from this surface to its center, say it's over here. So that is the radius of curvature there. I know those are overlapping, but I hope that makes sense. Okay, so the radius of curvatures of the two surfaces determine what the focal length of the total lens is. Okay, so one more thing I need to point out about radius of curvature is that it actually has different signs. So imagine my light is coming in from this side. I've got a lens right here, boom, like that. And I want to know what the radius of curvature of each of these sides are. So it's important to know that the direction that the light is going is considered positive. So if I draw the radius of curvature, we'll call it R, of this lens, let's say this is it, right here. This is the R1, radius of curvature for surface 1. Surface 1, surface 2. The radius of curvature for surface 1 is positive because it is going in the same direction as the light. Now, radius of curvature of surface 2 is negative, so R2 is actually negative, so I'll make a note of that. This is positive, this one is negative because it is pointing in the opposite direction that the light is going. That's important to keep in mind because when we do the lens maker's formula, which I'll go ahead and put up now, all right, the lens maker's formula is this. 1 over the focal length of the lens is equal to the index of refraction of the lens minus 1 times 1 over radius 1 minus 1 over radius 2. Okay, double check that. Good. This is the lens maker's formula. As you can see, it relates everything that makes up the lens, the index of refraction, so the material, and the shape of each surface, to how it behaves, the focal length. And generally, the focal length is something that we care about lenses, because say you're making glasses, you want to know what the focal length of that lens is, so you can get it right, so that the light lands right on the back of your eye. Okay, we can use this equation in other directions, though, if we want to calculate the radius of curvature. That's a little bit harder, but we can do it. We could calculate the index of refraction if we knew the focal length and the radiuses of curvature, which we're going to do in the end of the lab. Or we can use it just normally to calculate the focal length. So I'm going to walk through an example here because the sign conventions for R1 and R2 can be tricky. Okay, so we're going to use the lens that I drew up here, and I'll draw it a little bit bigger for our example. So I've got a convex lens like this. Boom. My light's coming in this way. This is my surface 1, this is my surface 2. I'm going to say that each surface has the same size radius of curvature. Just remember they go in opposite directions. And it doesn't always have to be the case that each side of the lens has the same curvature. But for our labs, that's the way that all the labs, that all the lenses in our lab have been set up. Okay, so I'm going to say that the radius of curvature for the first surface, R1, is 10 centimeters. Namely, it's positive 10 centimeters. And I'm going to say, let me remove that for clarity. So we'll say that light is going in this way. Then we're going to say that the radius of curvature of the second lens, or the second surface, R2, is negative 10 centimeters. Okay. Now, oftentimes when you do problems like this, they're not going to tell you whether it's positive or negative. They're going to expect you to figure it out on your own. So they would probably say that each surface has a radius of curvature of 10 centimeters. And it would be up to you to say, okay, the radius of curvature for surface 1 must be positive since it's pointing in this direction, the same direction as the light. And the radius of curvature of surface 2 is negative because it's pointing in the direction, or it's opposite the direction of light. As a side note, if we had a concave lens like this, the radius of curvature of this side is pointing back against the direction of light. So this is our light. So R1 is negative here, and R2, pointing in the direction of light, is positive. Just do it like that. Okay, so that's an aside. Make sure you keep in mind which direction your radius of curvature is pointing in order to keep those things straight. Oh, you know, the last thing I'd like to say about the sign convention too is that if I draw back in my concave lens, remember the light came out like this. The light was coming in straight like this. And we said that the focal length, the focal point was over here on the left side of the lens. So the focal length, which is the length from the center of the lens to the focal point, F, it follows the same sign conventions. So this is pointing in the opposite direction of light. So in this case, F is negative. Negative. Versus a lens like this where the focal point was out here somewhere, that was a positive focal length. Okay, that's important for the lab, so make sure you pay attention to that. Okay, let's continue our example real quick. We'll go through it. And I'm going to say that this is made out of acrylic, which is the same material we've been working with for pretty much all of these lenses. So the index of refraction of this lens is 1.5. So I'm just going to plug in these things and calculate the focal length. So remember, this is still 1 over the focal length. You get 1.5 minus 1 times 1 over radius 1 is positive 10 minus 1 divided by radius 2, which radius 2 is negative, so I'm going to do this. 1 over negative 10. I'll just put that in parentheses to make it clearer. Okay, so now, just messing around with my signs, this is just algebra at this point. I'm going to bring this negative sign out and make this whole term a plus. So now I get 0.5 times 1/10 plus 1/10. Now, this math should be easy from here on out. So we get 0.5 times 2/10. And now I'm going to use, remember 0.5 is actually the same as 1/2, just so I can do this in my head. 1/2, cancel my halves. And I find out that 1 over the focal length is 1 over 10. Now the focal length here, remember this is 1 over half. Okay, so this all tells me, and hopefully I'm not running out of frame here. Good. This tells me that the focal length of my lens is 10 centimeters. Okay, so that is just a coincidence that it is the same as the radius of curvatures, but remember, you can use this formula here to calculate it no matter what. Okay, great. Let's continue on. So that was our lens maker's formula plus example. Let's talk about the procedure now. Okay, so the first procedure is we're going to measure the focal length of a convex lens and a concave lens. Now, I want you to watch the video that I post the link to. I want you to watch that and see them actually carrying out the procedure in the lab. So you can see what it looks like for light really to pass through a lens. But here's the gist. This is what we're going to do. I'm going to walk through what the lab would look like on the board, which is not really a good substitute for a lab, but it's what we got. Okay, so imagine I have a light source. It's going to shoot out like 5 rays of light. 5. Okay, and I put a convex lens in front of it. Now, like I drew before, this light's going to come in and get bent down like this. I did an okay job of drawing it there. Oops, that was not good. And we say that, and this is our focal point, so we would mark on our paper exactly where this was, and then we measure with a ruler the distance from the center of the lens to the focal point. So this is my focal point F. We measure the focal length here, just like I was talking about before. Now this stuff's already going to be listed in the data sheet that I give you, so don't worry too much about, you don't have to actually measure this or anything like that. but I want you to see how it's done and what it looks like with real light, which is shown in the video. Okay, now the first thing I want to mention is that Sean, for his class, did it a little bit different. So he used two convex lenses right next to each other like this to demonstrate it. And basically what you end up with is just a shorter focal point. So it gets bent once coming through here, it gets bent again, and you end up with a focal point down here. For our class, we're only using one lens for this, and so our data will look a little different than his, but it's the same idea. So I still want you to watch the video to get the idea for how it works. But yeah, that's how we're doing it for us. That's our focal point. We're gonna repeat the same procedure with our concave lens, like this. And this one's a little bit different because as the light comes in like this, the light on the other side diverges. And so to measure our focal length, we actually have to trace these lines backwards. So the way that we do this is we draw these lines while the light is on, then we turn off the light. So this is all on, say, on a piece of paper or something. Turn off the light so we can't see these. We use a ruler or a straight edge or something, and we draw these lines backwards like this. And then we measure the distance from the center to this focal point right here. That was a little off right there. So that is also listed in the data sheet. Now, let me talk about procedures 1C and 1D. Now, those ones you do need to watch the video for because I want you to draw your own conclusion for what happens. But just to hint at what happens, I'll tell you a little bit about them. Okay, so now it asks, keep this light source on, but put a convex lens and a concave lens together. Okay, so convex lens right here. We know that if this was alone, the light would bend down like this. And we put a concave lens right next to it. And we know that when light comes through the concave lens, it gets bent back out. So what do you think might happen about these two, with these two lenses right next to each other? One bends the light down, one bends the light back out. You're probably already thinking of it, but they sort of cancel each other out. Now this is not obvious because we didn't see that these two lenses have the same focal length, but I'm just gonna go ahead and tell you that they do. And that's one of the questions, one of the results you're supposed to draw from this. But since we're not working on this stuff in the lab altogether, I'm just gonna go ahead and tell you that what happens is this lens focuses the light rays in, this lens spreads them back out, and what you end up with is the light passes through completely unchanged. Okay, and the reason for that is the focal lengths of these two lenses are basically the same, or close enough that the light comes back out in real life. Okay, good, so that's part C. Now, part D, the last thing, is it actually go back to just one lens. And what they're gonna show, and I do want you to watch the video to see this, but they say, okay, let's take a look at what this looks like with just the first three beams. So I'm gonna go ahead and just block off this beam and block off this beam. Just these three. And what you'll see is they converge at some point, just like normal. Okay, now what happens if I turn those three beams off? I'll keep that point that I just drew. Turn off those three beams and just turn back on the top and the bottom beam. What you'll find is something like this. The focal point is actually a little bit different from the top rays versus the middle three rays. Now the reason for this is this lens is not perfectly thin. All of our calculations assume that the lens thickness is actually 0, which obviously that's not true, and that should be clear when you watch the lab. The lenses are about probably that thick, something like that. But we treat them as thin lenses for our equations because it works out to be a really, really good approximation. But as you can see, it's not perfect. And when you watch the video, you'll find out that these two focal lengths are different. And the reason, again, is because the lens is not perfectly thin. Okay, so that's part D. So we just did part C, which you'll need to write your observations of from the lab. This is part D of number 1. Okay, the last thing I'd like to talk about are the I guess I shouldn't say the last thing, but now we need to talk about procedure 2, because this is where the mistake in the video was, unfortunately. Okay, so let me turn to procedure 2. So, procedure 2, one of the things we do in our labs a lot, you've probably noticed, is we like to calculate things different ways. So, we took those two lenses, the concave and the convex lens, and we measured their focal length directly, just by shining light through them, taking a ruler, measuring the focal length. Now, we'd like to measure the focal length, or compare the focal length, using the lens maker's equation. So what do we need to do for that? We need to figure out the radius of curvatures of those lenses. And I think actually in the lab it asks you to use the focal length that you found and the radius of curvatures that we're going to find right now to calculate the index of refraction. But in any case, we want the radiuses of curvature. That's what we're interested in. So there's one way to do this. There's not only one way. There's many ways to do it. The way that we're going to do it today is like this. And this is using a little bit of a trick, so I want you to pay attention. So, have our light source. We're shining all these beams out here, and we're going to, we're going to block out the middle 3 beams. We're just going to use the top 2 beams. So there's 3 beams here. We've just blocked them out. Okay, now we're going to use the concave lens, like this. We want to find out the radius of curvature of each surface. Now we're going to go ahead and tell you that the radius of curvature of each surface is the same, so if we find one, we find the other. Don't forget though that one's positive and one's negative. We're just talking about the magnitude here. So we want to find the radius of curvature of this first surface. Need a little bit more room here. So what we're going to do is this little trick. Here's my lens. I'm going to shine my light through these two. Bang, bang. We know that this light diverges out like this. Diverges out like this. A little bit stronger maybe. Now I told you that if you trace these lines backwards, these lines, remember, will meet way back out here at the focal point, F. However, if you turn off the lights, make it really dim in the room, and this is the mistake in the video, you can look at the light that actually bounces off this first surface only, okay? So when this light hits here, most of it goes into the lens and comes out the other side. But a little bit of it gets reflected. So this is the reflected light right here. And it comes down this way. The reflected light here comes back up this way. Okay. Now remember, the difference here is that this reflected light, this light is actually there. So that's why I drew it with solid lines versus the dotted lines. Remember, there's actually photons bouncing off of this surface of the lens and reflecting along this line. Contrast that with, there's no actual photons that follow the dotted line. There's no actual light coming from this point and going out. It's just how the light behaves, okay? The light that came into the lens from right here gets bent and comes back out as if it came from the focal point. But remember, it actually didn't. It came from this beam of light right here. That's important. On the other hand, the reflected light comes back off this way. And that's the reason that this light, the light that's reflected off this surface, does not land at the focal point, okay? So what we want to do here is we want to measure this distance, because we've now treated this single first surface as a concave mirror. So all these principles that we were talking about lenses, they're all based on the geometry of reflections, and that happens similarly with mirrors. So if you ever been to like a fun house or something like that, they've got those super wavy mirrors that make you look all like crazy shapes. That's because the curvature of the mirrors is different. They varied the curvature. The reason you want a perfectly flat mirror when you're getting ready in the morning or whatever is you want to be able to see yourself as you are, right, with no distortion. Having a curve distorts that light. So we say that this distance right here from the surface that we're treating as a mirror to the point where these rays cross, we treat that as the focal length of that mirror. Okay, treat that as the focal length of that mirror. So what we want and in the lab we went ahead and measured this. And this focal length of the mirror actually turns out to be half of the radius of curvature of that surface. So the radius of curvature of surface 1 is equal to 2 times this F mirror that I just measured. F mirror. Okay, so the focal length of this mirror, just to reiterate it one more time, is not the same as the focal length of the lens. The reason for that is the focal length of the lens relies on both surfaces reflecting the light. The focal length of the mirror is just the light reflected off of that surface. Okay, so now that we know that the focal length of the lens and the focal length of the mirror are different, we can continue on, and then you'll have to do some calculations. So one thing I could do is, now that I've found the focal length of the mirror, I can use that to find the radius of curvature of this side, and then we can find the radius of curvature of this side, and I could plug all that stuff back into my lens maker's formula and find the focal length of the mirror itself. Okay, and all this data has been taken in your lab. Okay, now that that's cleared up, it's okay if you still watch this section in the other video. It might be useful to see what I'm talking about the reflected light, but keep in mind the focal length of the lens is not the same as the focal length of this mirror we're talking about, which is the light bounced off the first surface. Okay, hopefully I've said that enough times that it sticks. Very last thing, I'd just like to make a note about procedure number 3. Procedure number 3 is basically just a utilization of lenses. We're not really calculating anything that has to do with the lens itself. All we're doing is, I guess I could have left that, but got my light source. I'm gonna block out the first 3 rays again, or the middle 3 rays. Take the last 2 rays, and we're gonna take that acrylic block from last week, that big old block. Let me make it a little bigger for example. And we put a lens right here, convergent lens. And what actually happens is we can focus the light right onto the point of this, right onto the edge of this surface. And then this light will get refracted as it comes back out. So if I trace this through here and here, then it gets bent a little bit more like that and like that. And if I trace these lines back into here, they meet at a certain point. Now I want you to watch the video about this and see how it happens. I want you to read through the lab manual to figure out why. They do give you the formula. Basically, this is called using apparent depth. So this is the same idea as when you look into a swimming pool or something like that, and the light that's bouncing off an object, like the object looks like it's closer than it actually is. Okay, this is just a quick note on this example, is that we're not calculating any of the index of refraction of the lens here. We're actually using the lens to figure out stuff about the acrylic block. Okay, and there's more on that in the next video. Okay, that is everything I wanted to talk about. Please feel free to ask me if you have any questions. I know that this week there's a lot of video watching. I apologize for that, but this is the best we can do to get you the information for this lab. Okay, good luck on the lab. Please feel free to contact me with any questions.